The concept of the multiverse, once a staple of science fiction plot lanes and speculative philosophy, has increasingly found its way into serious scientific discourse over the past few decades. Physicists and cosmologists from around the world have begun to consider that our universe, vast as it is, might be one among many. This possibility opens up a realm of extraordinary questions and implications, ranging from the fundamental nature of reality to the potential for collisions between these so-called bubble universes. One of the key pieces of evidence that has brought the multiverse conversation into the mainstream is a peculiar feature in the cosmic microwave background radiation, CMBR, known as the cold spot. Understanding how the cold spot might relate to the multiverse requires some background on the CMBR and why anomalies in it could be so significant. The CMBR is the leftover light from the Big Bang, originating roughly 380,000 years after the universe began. At that time, the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen, allowing light to travel freely instead of scattering off free electrons. This light has been traveling across the cosmos ever since, stretching into the microwave part of the spectrum due to the ongoing expansion of space. By studying minute fluctuations in the temperature and polarization of this background radiation, cosmologists can glean insights into the conditions of the early universe, as well as fundamental features of cosmological models, such as the rate of expansion, the distribution of matter, and the potential for exotic phenomena like alternate universe. When scientists map the entire sky in terms of microwave radiation, they note that the temperature is remarkably uniform, roughly 725 K above absolute zero, with tiny deviations on the order of microkelvins. These small fluctuations mirror the seeds of structure formation, such as galaxies and clusters of galaxies, which grow over cosmic time due to gravitational attraction. However, occasionally scientists have encountered anomalies, regions that deviate more starkly from the average temperature than standard cosmology would predict. Among these anomalies, the cold spot stands out. The mysterious cold spot, discovered in 2004, the cold spot is an unusually large and cool region of the CMBR. Initial attempts to explain it invoked the possibility of a supervoid, an immense region of space containing fewer galaxies and less matter than average. Such a void could, in principle, reduce the temperature of photons passing through it via the integrated Sachs-Wolf effect or related phenomena. Photons traveling through an underdense region might experience gravitational redshifting that lowers their observed temperature, although the specifics can get complex. For a number of years, many researchers remained convinced that the supervoid hypothesis provided a neat and relatively simple resolution. After all, large-scale structure in the universe can occasionally form vast voids. But as more data emerged, especially from comprehensive redshift surveys, suspicions grew that this explanation might not hold up. The Royal Astronomical Society's investigation, which analyzed some 7,000 galactic redshifts, failed to detect a supervoid in the region corresponding to the cold spot. Instead, they found only normal voids of the kind we see elsewhere in the universe, none big or deep enough to account for the pronounced temperature drop in that patch of the sky. The shift to a multiverse explanation. Once the supervoid explanation started to falter, scientists began to propose more exotic possibilities. Some speculated that the cold spot might not be a feature generated strictly by standard cosmology at all. Instead, they proposed it could be evidence of a bubble universe that once collided with our own in the very early universe. To understand this notion, one must consider the idea of eternal inflation. According to many inflationary models, particularly those pioneered by Alan Guth, Andre Linde, and others, the universe might have undergone a phase of exponential expansion, inflation, shortly after the Big Bang. In certain variants of eternal inflation, different regions of the inflating space stop inflating at different times, forming bubbles. Each bubble effectively becomes a universe in its own right, with possibly distinct physical constants and properties. Our observable universe would be one such bubble, surrounded, or at least in conceptual space, by many others. If these bubble universes can occasionally collide, it might leave an observable signature in the CMBR. Think of two soap bubbles expanding and then touching. At the point of contact, they would create a disturbance. In cosmological terms, that disturbance could appear as a temperature anomaly in the CMBR. Thus, the cold spot could be reinterpreted not as the effect of a void in our own universe, but rather as a collision scar, an inter-universal bruise, so to speak, left behind by contact with another bubble universe. Data from Planck and beyond. The European Space Agency's Planck mission, which gathered high-precision data on the cosmic microwave background between 2009 and 2013, with final results released around 2014, 2015, provided a wealth of new insights. Planck offered a clearer map of the CMBR's temperature and polarization fluctuations than ever before. In confirming the existence and characteristics of the cold spot, it added more weight to the notion that this region demands explanation beyond what standard cosmological models easily supply. Planck's high-resolution data showed that the cold spot was real. It wasn't a fluke of earlier lower-resolution measurements. With that confirmation, researchers delved deeper, examining whether the predicted supervoid solution might be consistent with the new data. Again, more refined analysis of galaxy surveys and improved cosmological modeling continued to find no evidence for a supervoid large enough to produce the effect. The mismatch between standard void scenarios and the cold spot's pronounced temperature deviation pointed more strongly toward an unusual cause. Probability and statistical significance. Science relies heavily on statistical reasoning to discern whether an observed phenomenon might arise by chance. According to the Royal Astronomical Society, simulations indicated only a 1 in 50 probability that the cold spot would form randomly within the standard cosmological model. While 1 in 50 is not astronomically small, it's also not so large as to make it trivially explicable. Typically, physicists look for odds of 1 in 100 or even 1 in 10,000 before labeling an anomaly highly significant. But 1 in 50 is more than enough to raise eyebrows, suggesting that a more extraordinary explanation could be in play. The key point is that if all other plausible standard explanations fail, no supervoid, no typical statistical fluke, then scenarios previously considered exotic become more viable. This is how the multiverse explanation gained traction among some cosmologists, although it remains far from universally accepted. What is a multiverse? The term multiverse serves as an umbrella concept for many different theoretical frameworks, suggesting that multiple universes might exist. Some approaches stem from cosmological inflation, leading to the idea of bubble universes as described above. Other versions derive from string theory's concept of a vast landscape of possible vacuum states, each corresponding to a distinct set of physical laws. Still, other perspectives come from the many worlds interpretation of quantum mechanics, which posits that every quantum measurement spawns a branching of realities, though that approach deals more with quantum states than with physically disconnected universes. Regardless of the path taken, these multiverse ideas share a similar implication. If true, our observable universe is merely one region in a much larger, and potentially infinite, reality. This radical shift in perspective challenges the notion that the Big Bang created a singular cosmic arena. Instead, it suggests that Big Bangs could happen all the time in different patches of an eternally inflating background, or that new branches of reality constantly split off due to quantum events. Collision signatures. The notion of bubble collisions providing a clue to the multiverse has been around for a while. In the early 2000s, theorists began exploring what such collisions would look like in the cosmic microwave background. Numerical simulations suggested that a collision might create circular temperature or polarization patterns, subtle enough that they could be missed if one wasn't looking for them, but distinct enough to stand out once you know what to look for. The cold spot, being a large circular area with a lower temperature, arguably fits the profile. However, distinguishing a bubble collision signature from standard cosmological fluctuations is tricky. The CMBR is a chaotic arena of overlapping signals, primordial quantum fluctuations amplified by inflation, acoustic waves in the photon-baryon plasma, before recombination, gravitational lensing, and more. Isolating a unique collision signature requires robust data analysis and theoretical predictions that can't be explained by simpler models. Skepticism and alternatives. While many scientists find the bubble collision scenario intriguing, there is still a healthy dose of skepticism. For one, cosmic variance means that certain anomalies may simply arise from the fact that we have only one observable patch of sky. Even if the probability of forming the cold spot by chance is relatively low, is not inconceivable that a few rare features appear across the entire sky. Secondly, some argue that improved data or new methods could yet discover a more mundane explanation. Perhaps a more subtle void, or a cluster of smaller voids that collectively mimic a single large void. Or perhaps there is a slight unknown systematic error in how the temperature of that region has been measured. Researchers from Durham University and other institutions continue refining their analyses, trying to tease out these nuances. Moreover, the idea of a collision with another universe conjures a variety of open questions. If collisions can occur, how frequent are they? Would multiple collisions appear in the CMBR? If bubble universes have different laws of physics, could they even meaningfully interact with ours? Some theories say collisions would end inflation in those regions, merging the bubbles into a single domain, while others suggest collisions might be lethal for one or both universes. The complexities run deep. The significance of redshift surveys. One of the main tools used to investigate the cold spot, or any large-scale structure phenomenon, is the redshift survey. When astronomers measure a galaxy's light spectrum, they see characteristic absorption, or emission lines corresponding to chemical elements. By noting how far these lines have shifted toward the red end of the spectrum, they can gauge how fast that galaxy is receding from us, which correlates with distance in an expanding universe, according to Hubble's law. The Royal Astronomical Society's survey of 7,000 galactic redshifts in and around the cold spot region was a key turning point. If a supervoid existed, researchers would expect to find fewer galaxies, and those galaxies might cluster in a specific pattern that significantly departs from average distribution. But that's not what they observed. Instead, they found normal or mild underdensities that didn't add up to a giant cosmic void. This discrepancy between observation and the supervoid hypothesis left the door wide open for alternative interpretations, like a bubble collision. Why the multiverse matters. The possibility of a multiverse is more than a cosmic curiosity. If multiple universes exist, each might harbor different fundamental constants and laws. For instance, one universe could have a slightly different gravitational constant, or the masses of subatomic particles might vary. Some universes might collapse quickly, others might never form stars. Our universe appears finely tuned for life, prompting many to wonder if this fine-tuning is less miraculous under the multiverse assumption. If there are countless universes with randomly assigned parameters, we happen to find ourselves in one of the rare universes suitable for life. Additionally, discovering direct evidence for other universes would revolutionize physics, cosmology, and even philosophy. Questions about the nature of reality, free will, and the scope of observational science would be re-examined. Could we ever travel to or interact with another bubble universe? Most mainstream theories say no, because once inflation ends in a bubble, it's causally disconnected from other bubbles. Yet the potential cosmic collisions posited here offer a tantalizing mechanism for at least minimal contact, a fleeting brush at the boundary that leaves an imprint in the CMBR. From science fiction to scientific inquiry. Just a generation ago, serious discussions about parallel universes or a multiverse were rare in mainstream science. These ideas resided primarily in the realm of science fiction, or were relegated to highly speculative corners of theoretical physics. Yet as more observational data accumulates, from the CMBR to large-scale structure maps to high-precision measurements of cosmic expansion, those once fringe theories have gained a stronger foothold. Ongoing research and future prospects. While the conversation around the cold spot has slowed a bit since the mid-2010s, it remains a subject of intense analysis. Researchers continue refining galactic surveys, hoping to get a more precise map of the region's matter distribution. Some also look for secondary signatures, a polarization imprint or gravitational lensing anomalies that might bolster or refute the bubble collision hypothesis. Meanwhile, new generations of telescopes and instruments are coming online. The James Webb Space Telescope, JWST, though primarily aimed at infrared observations of distant galaxies and star-forming regions, may contribute data on galaxy distributions relevant to understanding cosmic structures. Next-generation CMB experiments, like the Simons Observatory or CMES-4, aim to measure the microwave background with even greater precision, potentially identifying more anomalies or clarifying existing ones. If more anomalies akin to the cold spot are discovered, each might lend weight to the idea that our universe has had contact with others. Alternatively, if future data unambiguously explains the cold spot through some revised standard cosmological process, the bubble collision scenario might be relegated to the back burner once more. That's the nature of scientific progress. Each discovery either supports, challenges, or refines current theories, gradually painting a more accurate picture of reality. The broader impact. Should the multiverse idea gain widespread acceptance on the back of more robust evidence, the philosophical and cultural impact would be immense. The notion of a near-infinite collection of universes, each with its own laws and events, challenges many assumptions about uniqueness, destiny, and cosmic singularity. Our anthropocentric biases, that we exist in a one-of-a-kind realm, would be severely undermined. It might also shift how scientists approach fundamental questions about why physical constants take the values they do. If we live in a single bubble among countless others, the question of why these values might be replaced by We see these values because they're consistent with observers like us existing in this bubble. Even the language used in cosmology might change. We currently refer to the universe as the totality of existence. But if the multiverse is real, then universe becomes more of a local, bubble-specific concept, and multiverse becomes the overarching reality. Popular culture has already embraced these themes, as evidenced by countless books, movies, and television shows exploring parallel worlds and timeline. Looking ahead, ultimately, the cold spot stands as one compelling piece of a much larger puzzle. While it hasn't conclusively proven the existence of a multiverse, much more data and theoretical development are required. It has opened the door to the possibility that our cosmos may be far stranger and richer than once believed. Physicists and astronomers remain cautious, as extraordinary claims require extraordinary evidence. Nevertheless, the bold hypothesis that we might be living in one of countless bubble universes has moved from speculative lore to an active area of research, fueled in part by this peculiar temperature anomaly. We must remember that science evolves through iterative processes: observation, theory, prediction, and refinement. Just as the Copernican revolution displaced Earth from the center of the cosmos, the discovery of dark matter and dark energy revealed we're only familiar with about 5% of the universe's composition. Now, a possible next step in cosmic humility might be learning that our entire observable universe is but a single bubble in an infinite expanse, one of many. If the cold spot is indeed a bruise from a collision with a neighboring universe, then future analyses might identify more such bruises, each reinforcing the case for a multiverse. Conclusion: in sum, the cold spot's discovery and subsequent investigation represent a vital chapter in the ongoing quest to understand the fundamental nature of reality. Initially labeled a supervoid, the region at first appeared as a statistical quirk, something that might be explained by ordinary cosmic structures. But deeper surveys challenge that explanation, showing that the region's temperature fluctuations are not readily accounted for by standard cosmological models. Instead, researchers began entertaining the possibility that we're seeing evidence of a collision with another bubble universe. Though definitive proof remains elusive, the cold spot has spurred some of the most intriguing discussions in modern cosmology. The Planck mission's confirmation of its existence, combined with redshift surveys that rule out a simple supervoid explanation, have brought multiverse theories onto firmer observational ground. The Royal Astronomical Society's statement that there's only a 1 in 50 chance of the cold spot arising randomly underscores the anomaly's significance. Should future studies corroborate that this anomaly really does result from an interuniversal collision, it would mark a turning point, offering the first direct, empirical clue that our universe is not alone. On the other hand, if ongoing or future research finds a more mundane explanation, the scientific method will have once again self-corrected. Either way, the cold spot controversy showcases how cutting-edge astronomy and physics can push boundaries, taking ideas once relegated to speculative corners and placing them at the heart of mainstream scientific discourse. Whether the multiverse exists or not, the process of investigating anomalies like the cold spot expands our understanding of the universe and refines our theoretical frameworks. As new telescopes, satellites, and surveys come online in the coming decades, we may be able to explore the cosmic microwave background with unprecedented clarity. Each new advance has the potential to either strengthen the case for bubble collisions or discover alternative phenomena that shape our cosmic perspective. Whichever path the data ultimately takes us down, one thing is clear: we stand on the cusp of a revolution in cosmology, where the possible reality of multiple universes is no longer mere fiction, but a realm of genuine scientific inquiry. And so, the story of the cold spot continues, a symbol of how one small patch in the cosmic microwave background might hold keys to an almost unimaginable grander reality. We may find that our universe is just a leaf on an immense cosmic tree, or we might discover that such collisions do not happen. Either outcome will sharpen our understanding of who we are, how we got here, and just how big or varied reality might be. In that sense, the cold spot is more than a temperature anomaly. It is a window into the fundamental nature of everything we know, and possibly everything we've yet to discover.